Okay. Good afternoon, everybody. My name is Derek Dazenbrock. I'm a member of ASCE GI, and I serve on the Geo-Institute's Technical Coordination Council. I was also the chair of the 2020 ASCE Geo-Congress, and it's my pleasure to welcome you today to the second of our student research webinar series. I'm going to share some content as we kick off our presentation today. And hopefully everybody can see the screen. Today we're going to be joined by several speakers talking about some of the current work on the Geo-Institute's special projects. I'd like to thank you for joining us today. As I mentioned, this web event is part of a series. It's the newest addition to the Geo-Institute's student activities. And the student research series is where we recognize the importance of collaboration, communication, and the role of the research community. We're providing an opportunity for our student researchers to present in-process work and practice presenting in front of peers and to a wider audience. The topics for the webinar series are expected to rotate, and you'll be seeing different GI technical committee members assisting, both supporting and moderating the sessions. Check back to our webpage and certainly the announcements in Geostrata for the next sessions, which will be occurring throughout the year. I'd like to thank our presenters today and just mention a few things before we get started. As I mentioned, the presentations in this series are going to be related to GI's technical committees. We have 20 of them. Ranging from computational geotechnics all the way down to unsaturated soils, as you can see on the list there. Event partners also include the GI's Student Participation Committee, our Student Leadership Council, and our Continuing Education Committee, all committed to overall student participation, leadership, and education. Quick note that the ASCE Geo-Congress 2022 is coming up next week. It's an in-person event. It'll be in Charlotte, North Carolina. We're expecting over 1,000 geoprofessionals, manufacturers, contractors, researchers, and students. There's still time to join us for that event at the Charlotte Convention Center. Main focus topics are the state of art and state of practice in geotechnical engineering, and more information is available at geocongress.org. Would also like to take the opportunity to mention our Student Participation Fund, a great way to support GI students and the student activities, many of which are held at the Geo-Congress. I would like to make a special note that the 25th anniversary, our silver anniversary match, which was throughout last year, 2021, is now being extended, carried over into 22 through March. So head on over to the GI website, look for the Student Participation Fund up in the top frame, click on that, and there are multiple ways to participate, either as an individual or as an organizational sponsor, as well as considering a sustaining membership, $96 annually. You get a thank you gift each year, and this year it's our Terzaghi bobblehead. So with that, I'd like to introduce today's session moderator, Dr. Nick Hudyma. He's a professor of civil engineering at Boise State University and is chair of GI's Technical Coordination Council. His personal research interests include characterization and investigation of geohazards of rock, and in his spare time enjoys cycling, ice hockey, and hiking with his dog, Asta. So with that, Nick, I'm going to turn it over to you.
Awesome. Thank you, Derek, for the kind introduction. It's a pleasure for me to be here today, especially supporting our students who have worked very hard on their special projects. Just a quick reminder, special projects are sponsored by the Geo-Institute, and the special projects work is performed by technical committees, and we're hoping that the special projects actually support student work. And we have 3 prime examples of student work associated with special projects today. Just a quick note, please place your questions for the students in the chat, and there'll be some time for students to answer the questions after their presentations. And then at the very end of our session, we'll have more time for more questions and answers. I'm going to share my screen now. There we are. And we're almost ready to start. Our first presenter is Melissa Hancock. Melissa received her undergraduate and graduate degrees in civil engineering at Boise State University. She conducted research and assisted in projects to integrate sustainability and resiliency topics into civil engineering. Her master's thesis topic was developing implementable strategies targeting sustainable building construction through international policy diffusion. She worked with Dr. Chitori on this research. Unfortunately, she's left Boise, big loss for Boise and the Treasure Valley area, but she got an awesome job in Nashville, Tennessee, working as a traffic engineer at the Department of Transportation. Melissa, I will turn everything over to you right now.
Thanks, Nick. Good to see you too. All right, let me share my screen. And you guys see the slide, right? Okay. All right. So I'm Melissa, and I worked on this project with Dr. Chitori over the course of my master's degree, which was sustainability and geotechnical engineering, was the topic of this project, and we developed this module for the Geotech Tools website. This was with the Sustainability and Geotechnical Engineering Committee, and this committee's goal is just to promote the role of geotechnical engineering in improving the quality of life through balanced consideration of the economy, the environment, and society. This committee has a membership of over 30 members from the industry and from academia, and Dr. Chitori is the chair. And we'll begin. So just the layout of this presentation, I'm just going to go over the background on this project, and then start talking about the details of sustainable development, geotechnical sustainability, assessment tools, and then a case study on using the tools. So, important topic, what is sustainability? I'm sure many of us have heard of this term. Basically, sustainability is just meeting the needs of our present generations and maintaining those same needs for the future. So this is done through maintaining the balance between these three environment, social, and economic aspects. And the main point is that everyone has an equal opportunity to maintain their quality of life without diminishing their available resources. So here are some key terms that are important to this topic. A life cycle cost or a life cycle assessment is just a way to assess environmental impacts throughout a project's lifetime. The life cycle cost assessment is similar, but it's assessing and comparing the project alternatives, their lifespans, and the related costs in order to determine which is the most cost-efficient option. And then ethics and sustainability is also important. ASCE, the American Society of Civil Engineers, has outlined that all engineers should create safe, resilient, and sustainable infrastructure. So along those lines, ASCE has a couple policies that are based around sustainable development. So the first policy that's listed here, it discusses engineers' role in sustainability throughout projects, the use of the life cycle assessment, and maintaining societal equity and resiliency throughout all projects. And then the second policy there, it also outlines our responsibility as engineers to supply solutions to our clients for basic human needs that preserve environmental diversity and resources to use them sustainably. So moving along on a global level, the United Nations has created this Sustainable Development Goals to outline key targets for governments worldwide to strive for in development. This group that came up with these goals categorizes or uses these 17 targets here to rank 165 different participating countries on their sustainable development. And they have a whole report that comes out each year. I believe 2020 was also in there, but that year some things weren't done. So anyways, but it's pretty much every year that they rank all the countries, and the countries can all use this outline that the UN has set up to enhance their society and development and strive for sustainability. So it's very good and important. These goals aren't all specific to civil engineering and geotechnical engineering, but there are some that are more geared, or geotechnical engineering has a part in these. So this is where we come in. So some sustainable development principles I've outlined here. Stakeholder involvement is important. So engineers should involve the stakeholders early with plans of incorporating sustainability into the development. This collaboration is important to successfully incorporate the sustainability and keep them in the loop on what our goals are and how they can align with the client's goals as well. Site characterization, appropriately picking the right site and understanding the different aspects of the site will help us pick the right alternatives for the development. Optimal use of materials and energy throughout planning, design, and construction, and maintenance also goes along with sustainable development. Project resiliency and redesigning if the infrastructure is projected to fail with any natural disasters or other disasters that might be inflicted on the project. Minimizing the negative impacts that a development might have by using materials and methods that can cause, or using materials and methods that can cause negative impacts. So minimizing those to our best ability. And then reuse of existing and geotechnical elements can also minimize waste, which I'll talk more about that one in a bit. And then finally, appropriate instrumentation, monitoring, and maintenance throughout the project to ensure proper functioning of its facilities and processes throughout the development process. So here are some examples of how geotechnical engineers can contribute to sustainable development. So recycled materials, coal and fly ash, recycled glass, crushed rock blends for pavement subbase applications, mixed glass and plastic in segmental retaining walls, just reusing materials that are already there and recycling them into new projects. Alternative techniques, so for ground improvement, alternative techniques like these can all provide economic savings and reduced carbon footprints. So there I've written out some different sustainable ground improvements, the deep dynamic compaction, and you can read those all there. I don't need to read them all. And then reusing and recycling existing foundations is one example of that. Reusing and retrofitting existing foundations cut costs. They can cut the impacts and reduce disturbances that construction can have on nearby neighborhoods. And then Also, some things to consider: removing an old foundation could cost about 4 times as much as reconstructing an existing pile foundation. And that's not taking into account any of the potential damage that could be caused from demolition to nearby buildings and backfills. And then I've already talked about life cycle assessments, but these can be used to assess the sustainability of project alternatives. And then finally, underground space and usage. This is becoming more popular in the recent years. Many countries have already implemented this into their developments, like Hong Kong, Japan, and Singapore. Projects like this include underground hydropower houses, telecommunication centers, storage, and wastewater treatment plants have all been done underground and successfully. So here I'm going to talk a little bit about resiliency and sustainability. So here's a chart about the time that has to do with resiliency of a project. So resiliency is the ability to bounce back from any hazards or incidents that can happen to a development or infrastructure. Resiliency has 4 different aspects to it. They're also known as the 4 R's of resiliency. So robustness, redundancy, resourcefulness, and rapidity. So robustness is the ability of the system to withstand stress and demand. Redundancy is the measure of how well a component of infrastructure is suitable in the event of damage. Rapidity is the capacity to mobilize resources in the event of disruption, and resourcefulness is a capacity to mobilize resources in the event of disruption. So here you can see at the beginning of the graph, the infrastructure is in its normal state, and then circled there you see a disruptive event occurs. The efficiency or effectiveness of that system goes down and starts to not function as it is supposed to. And then that flattened line there is its fully disrupted state. And then with the resiliency, we can see that it the system will start to recover and then finally get to a stable recovered state. So yes, this chart is just showing the time of a resilient structure. So there'll be a period of time that the system is declining in its function. It'll be not functioning like as well as it needs to be for a period of time, and then it should start recovering and be fully recovered. In some cases, resilient structures should be able to maintain their functionality throughout a disruptive event. Sometimes that's not possible. So the time that's related to resiliency of the infrastructure is important to maintaining our structure's functionality. So resilience works hand in hand with sustainability, which is why I'm mentioning it, and it's mentioned in our project, as it impacts the public with its functionality and is one of the 3 sustainability pillars. So here is the overall geotechnical design stages currently. So we have geotechnical planning, material characterization, analysis, design, construction, and geotechnical, the product. It's suggested to add in a sustainability assessment in between design and construction. That way we can apply our sustainable solutions into the construction phase and have a more sustainable product. So moving on to some of the sustainable assessment tools that are out there now. I'm sure some of you have heard of at least the LEED certification. So these aren't specific to geotechnical engineering. They're just sustainability assessment tools in general. And we can use these as a basis on building off of and making more specific to geotechnical or adding geotechnical engineering aspects into these. But so I'll just go over what these basically are. The LEED certification is just a green building certification program. It rates buildings based off of their the sustainable sites, water efficiency of the infrastructure, energy and atmosphere that's involved with the infrastructure, materials and resources used, indoor environmental quality, innovation, and design process. And that design has to do with geotechnical, so that can kind of be linked there. Envision is an infrastructure rating system to evaluate and recognize projects for their contributions to a sustainable future. BREEAM is a it stands for Building Research Establishment Environmental Assessment Method, and it's for new and existing buildings. And then Green Roads is an internationally recognized sustainability assessment tool for transportation infrastructure. So finally, I'll wrap up with this last case, or with this case study on collapsible soils, ground improvement techniques. So this case study was a large warehouse development that was being built on top of a site in the American Southwest that had collapsible soils. And this is common for this area. They had a goal of maintaining a 5,000 pounds per square foot bearing capacity, and then also to be sustainable. And this project was another target that the client and engineer had on this project. So their ground improvement techniques that they looked into and analyzed was to over excavate and compact the vibrostone columns in deep dynamic compaction. And then they also did a carbon calculation of each of those techniques. So here on this slide is a clip. The rest of the chart is on the next slide. But so this goes over all the project alternatives. You see those three across the top there, and the different inputs that were analyzed. So you can see materials here. So we have water. The first option uses a lot of water. The second and third options don't use water. And then we have the other things on the left side there that are all incorporated. The work days are an important aspect because clients may have a very strict timeline. So that is part of their considerations in choosing which technique to go with, and then how big their workforce needs to be. And then here it's just continued, the different materials on the side, how they compare between the different technique options, the waste involved with each option. As you see, the second option there, what has a lot of waste involved. So the conclusion of this project here, these pie charts show the breakdown of where their carbon emissions are coming from. So you see waste here is the biggest, or I think that's energy. Sorry, my screen's a little small. But yeah, so you see the breakdown here, and on the right of those pie charts, it shows what each of the colors mean, and then each technique there. So by completing this study and presenting all of the details to the client, the engineers were able to explain the differences between the techniques, their pros and cons, allowing the client to make a better decision that was more educated. And yeah, so the research has also shown that concrete and steel methods of ground improvement have bigger waste and carbon emissions connected to those techniques. So these different ground improvements techniques are a little more environmentally friendly. The the deep dynamic compaction ended up having the least amount of carbon emissions, but that project schedule had a long, it had a longer time period. It was 9 weeks compared to the vibro stone columns, which was 8 weeks. And then the over excavate and compact had 12 weeks. So I think in this scenario, in this scenario, the client chose vibro stone columns since it had the least amount of time. And then its carbon emissions were about the same with the over excavate and compact method. So yeah, the second option was what the client went with. And then it's noted that this case study did not have a reliable way of measuring impacts on the neighborhoods and the societal aspect of sustainability. So this can be hard to measure, and research has been going on how to better measure the societal impacts. But further research is needed to find the best solution on measuring the societal impacts for sustainability assessments. Yeah. So in summary, geotechnical engineers contribute to a wide range of infrastructure sectors, as our designs are the foundation of all projects, literally. There's a great opportunity because of this for us to take a part in this transition to a more sustainable future in development. And using these resources that we've compiled and building off of them, doing further research and advocating for sustainable design and practice is crucial to our success in implementing sustainability into our field, and also to spread to other aspects of engineering and lead the way. So that is it. Thank you for listening and watching. And I think now is the time for questions.
Thank you very much for listening.
Thanks.
That was a very interesting talk. I don't see any questions in the chat as of yet, but I'll ask you a question.
Okay.
So, based on all of your experience now, which was your favorite calculator that you used for sustainability calculations?
So it's hard to say because none of the calculators that I came across accurately measure the societal impact. Like I said, it's really hard to measure that in general, and there isn't like a basic, there's not something out there that everyone uses that's wide used to measure. But I guess the one that is easiest to understand and like comprehend is probably the LEED certification. I just wish that one also took into account the economic aspect of the project. As far as I know from the research I've done, it doesn't take that part into account. It's mostly focused on the design of the building or the infrastructure itself. So yeah, probably that one, but yeah, I guess that's the best answer.
Awesome. Thank you very much. Great presentation. And of course, thank you for mentioning underground space. Right?
Yeah.
That's our realm, right? Is the underground. So it's I'm very happy that you mentioned that.
Yes.
Okay. So what we're going to do now is have an introduction to our next speaker. And here he is. Our next speaker is Flynt Tuller from Rowan University. He is an undergraduate student, which is fantastic to see undergraduates participating in our special projects. He has been working as an undergraduate research assistant since 2020 and is actively involved in the Geotech Tools project to develop a technology catalog for rock slope stabilization. He has a number of years of leadership experience, and he is the president of Rowan Chi Alpha. Flint is working with Dr. Zhu, an active member of the Rock Mechanics Committee. So, Flint, the cloud is yours. Proceed with your presentation.
Thank you so much. Before I begin, just a little disclaimer. I think I might be having some network issues. So if at any point my screen isn't sharing or I'm breaking up a little bit, feel free to stop me, let me know. I don't want to continue presenting while people aren't able to hear what I'm saying or see what I'm talking about. So with that being said, like I said, my name is Flint Tuller. Today I'm going to be presenting on the development of a Geotech Tools technology catalog for rock slope stabilization. I'm presenting on behalf of myself, Ryan Eno, and Dr. Cheng Zhu. Before I begin, I'd just like to give some acknowledgments and special thanks to the American Society of Civil Engineers, the Geo-Institute, and the American Society of Civil Engineers, the Rock Mechanics Committee, for whom this research was funded. Quick introduction to myself, a lot of stuff that you just heard. I'm currently a senior at Rowan, seeking a Bachelor's of Science in Civil and Environmental Engineering, graduating in May. I currently have two research interests on campus. Rock slope stabilization is the first, of which this presentation is about. The second one is on frozen soil characterization. This is also research that is done underneath the tutelage of Dr. Cheng Zhu and working with other undergraduates and PhD students on campus. And then, of course, when I'm not doing academic work or research work, I'm serving as the president of Rowan Chi Alpha. Now, kind of moving into an outline of the presentation, I'm going to be starting with the background on what Geotech Tools Technology Catalog is and some of the existing documentation. So beginning with the technology catalog, essentially the goal of this technology catalog, for those who are not familiar with it, it allows there to be a kind of all-encompassing list of a bunch of technologies that are used for either soil improvement, rapid embankment construction, or stabilization of the pavement working platform. It's a place where engineers who are working on different projects that involve the geotechnical side can go to, because they might not be familiar with certain technologies, or they might want to kind of brush up a bit on some information about some of the specific ones, or even look into what technology would work best for their specific project. So this is kind of an all-encompassing source for that. Moving into the existing documentation. So currently, rock slope stabilization and the information about it comes from two main locations. The first is academia. You have your textbooks and your journal articles. And then the other, more of the specification side, you have your laboratory specifications, and then different state DOTs will have different published specifications as well too. A couple federal sources, but not many. So essentially going into slope instability, what causes them, and kind of the background for why stabilization is needed. The two main causes are either active construction, if on a job site, the engineers know that they're going to be doing something with a rock face that is going to cause instabilities, they can plan ahead of time and start using some of these stabilization methods as they're going through the rest of the construction process. Or for a rock face that is subjected to some kind of weathering, or there's natural disasters in the area, that can cause some unexpected instabilities. And then that really breaks down what stabilization is. You have your preventative stabilization, which is in tandem with construction, and then you have your remedial stabilization for when you're not really expecting those instabilities, or they're caused by natural disasters or different things like that, where you then have to react to them after the fact. Now, kind of moving into the next stage, we're going to be talking about our design guidance. The outline of this report also is following the outline of the Geotech Tools catalog, so a lot of these same categories can be found there as well too. The first one I'm going to speak on is rock bolts. Rock bolts are kind of the gold standard of slope stabilization. They're the technology that's been around for the longest, that are used most commonly. Essentially what they do, they prevent the sliding of blocks or wedges within the rock face. They will have a bolt that is shot through the instability section of the rock face into a stable part behind wherever the instability of the rock mass is. It'll anchor in behind there, and then there will be a compressive force that is induced on that unstable mass, and it will bring it together and cause it all to be grouped into a tighter fit, and add that extra stabilizing measure. So there's four main parts to rock bolts. You have your reinforcement element, which is the bolt itself. It's going through the center of that unstable rock mass. You have your internal fixture. Oftentimes it's grout or a mechanical anchor of some kind. That's what's going into the stable rock mass behind the instability. You have an external fixture, which is a faceplate and a nut. This will be a little bit on a larger side, but that is the face where all the compressive force is being driven into the outer section of the instability. And then, of course, a rock mass is needed as well, too. Otherwise, compressive forces wouldn't be generated. The next section and technology that I'm going to go over is tieback walls. Essentially, what tieback walls are, they're pre-stressed steel tendons with walls, beams, and concrete blocks. Now, tieback walls are used alongside rock bolts. This is for areas of rock mass with greater instability. It's not just in one specific section. You're worried about a larger area of instability. And so this allows for that force, that compressive force, to be spread out much more and to be a lot more like all-encompassing when stabilizing this section. And so this is used in the same way as rock bolts, but just for a wider scope, a wider area. Now, I can't really talk about rock bolts and tieback walls without talking about shotcrete. Shotcrete is very important because it's utilized alongside these other two measures. Shotcrete itself is not a stabilization measure, but it's more of a preventative measure that works alongside these other stabilization measures. When rock bolts and tieback walls are installed, a hole needs to be drilled. They're shot through this rock mass. Shotcrete is responsible for kind of placing a layer over top of everything there. So what it allows for is it allows the lifespans of these rock bolts and tieback walls to be extended because they're now protected from weathering, from different corrosive elements, and essentially allows them to be isolated into the area that they're needed without being subjected to outside forces at all. Now, shotcrete's also always used with drainage. This is very important, which I'll talk about next slide, of course, as well, too, just because shotcrete takes away all the holes, and so you need a place for the water to escape. But essentially, the installation for shotcrete, you're going to make sure that you're using scaling, you're taking off all the outside debris, you're dampening down the area so that way it can bind to it a lot easier, and then you're putting some kind of frame or reinforcement, and then you're spraying it over the area that you want to cover. And then moving into horizontal drains is the last of technologies that I'm going to talk on today. Specifically, horizontal drainage for rock faces is very different from soil systems. Drainage for soil systems, you're working where water is permeating through everything. You have a water table, and you are needing to find ways to drain the water from all areas of a system. Rock faces, they're impermeable. So the water is really just building the pore pressure in the slope failure geometry, and where it's actually infiltrating into the rock face itself. Unfortunately, this means that for horizontal drainage being used as a stabilization method, It's very much a case-by-case basis. There's no one size fits all for these projects because they're so dependent on what that failure geometry is or where that groundwater infiltration happens. But that doesn't mean that it's entirely guesswork. There are several design specifications that basically apply to almost everything. You have a 5% downward slope, which can kind of be seen in that top right picture. Pipes are generally somewhere between 3 to 10 meters away from each other, and they're usually placed between 1/3 and 1/2 of the height of the rock slope, so that way the water can sink downwards and then drain out through the base of this rock mass. I'm now going to move into the specification section. This is really the true weight of the research that we're doing here. And so first I'm going to talk about our cost information that we gathered. So the interesting thing about this is that very few sources actually include the cost information. All the data is coming from different case studies or federal bids. It really doesn't get talked about a ton, and a lot of the academic sources will talk about how they're utilized, but less of the concretes, which is the prices and the quantities used. So for the first one, our rock bolts, we have a source from the Virginia DOT in 2006, where they utilized 600 linear feet of rock bolts in their project. We have a low unit price of $80 per linear foot, a high unit price of $100 per linear foot, so there's a bit of variation there. That same Virginia DOT utilized Shotcrete as well. They used 4,200 square feet of Shotcrete in this project, and that was just one solid unit price throughout, which was $55 per square foot in that project. And then finally, the horizontal drainage. As you can tell, this is something that there's not that much data about, kind of what I touched on before. The source that we have for this is the USDA Forest Service, and that's from 1987. And so there's a couple cases where they used it and they documented it. You have one where they used 2,754 linear feet of drainage, and that generated a low unit price of $10.89 per linear foot. Then you have a higher amount, 7,800 linear feet of drainage, and that generated a higher unit price of $14.68 per linear foot. But that is, you can tell the sources from the 80s. There's not much information from horizontal drainage use out there, and really lacking in anything recent. And this is taking even a step farther with tieback walls. You'll notice that's one of the things that I talked about before. It's not listed here. We weren't able to locate any sources that gave a concrete cost for tieback walls or their installation beyond just various case studies talking about it or academic sources explaining what it is and how it's used. Now, moving into the quality control, quality assurance section, all of these different technologies have different QC/QA methods, and some of them are standard specifications that are accepted everywhere. Some of them are very much theoretical that are hoping to be standardized at some point. I'll start with our rock bolts. Like I said in the past, this is kind of the gold standard. It's been around for a while. So they have the pull test, which is an ASTM standard from 2013. This is something that you can reliably use, and everyone follows the same guide. But then moving into the tieback walls, they have their ground anchorage integrity testing method. And the source and the reference for this is a journal article. There is no standard specification currently that is kind of universally accepted. This is a newer QC/QA test that has come about. It's from 2019. And so while it's gaining steam and is being accepted, it doesn't have that same reliability as like an ASTM or an ACI, which is the next one. For our Shotcrete, we have our compressive strength testing for the concrete used inside there. The source for this is the American Concrete Institute. It's another one that's been around for a while, widely accepted specification. So there's more reliability with that as well too. But then going to the horizontal drains, we're going back again, similar to tieback walls, you have a water pressure monitoring method, but this is coming from the rock slope engineering textbook that is on its 5th or 6th edition now. And while that's a widely accepted source, it's not held in the same weight as some of these other specifications. Now, moving into the case study section, I'm just going to talk about one case study today. There are many others kind of considered in our actual research, but just for the sake of time, I'll be talking about the rock slope stabilization evaluation, design, and construction in Greater Boston, Massachusetts. This is the most recent case study that we considered. This is from 2018, and specifically this situation happened where there was a condominium that was built in front of a rock mass, and over time that rock mass was found to have some instabilities. Rock falls were occurring, and so engineers were brought in to stabilize it after they used LiDAR technology to kind of gauge everything and find out the data behind it. They decided to utilize rock dowels, anchored wire mesh, anchored drapes, and scaling on it. Scaling, of course, just being an external method that we're not really talking about today. And of course, rock dowels, no real surprise to find them here. So I've said a couple times, they're kind of the gold standard. They're the most well-known and the most utilized. And then finally, I'm going to go into kind of the conclusions from this research specifically. Rock slope stabilization really is a preventative measure first and foremost. When you know that you're going to have a construction project that is going to cause slope instabilities, you're going to be planning stabilization methods as soon as you're planning the rest of it as well too. But that doesn't mean stabilization can only be preventative. It is also implemented for unexpected slope failures or for after the fact, though it was noted that stabilization works best when it's preventative, simply because for rock masses, once they start to relax, you have their different shear strength decreasing. There's no way to get that back. So when it's used preventatively, it's much higher effectiveness. There's also, just looking at the stabilization as a whole, a couple different technologies. I just talked about 4 today. There are many more than that, but those are the 4 that are most seen, though some of them are still on the newer side or don't have as much documentation about them. They can be used independent of each other, or they can be used in tandem. Different projects require different things. Now, rock bolt, shotcrete installation, those are used together quite commonly. It's known that if you're going to be using some kind of rock bolts, you're going to want shotcrete as well too, to keep it safe. Whereas tieback walls, that's not used as commonly, so there's not as much documentation that exists about that technology. Finally, the information on rock slope stabilization really mainly lies in the academic world. There are definitely case studies that exist about it, and there are absolutely specifications from different state DOTs or other sources like that. There's no universal standard. There's no federal document or specification out there that is all-encompassing for every type of slope stabilization method. That means that for engineers who are wanting to use more than one technology on a project, they have to bounce around to different places to find different specifications, different specifics. And so the hope is that one day, sometime soon, we will get some kind of universal standard that will allow engineers to be able to use this information in a much more streamlined way, and they can go to one source and know that it's all been tested, all been accepted in the same way, as opposed to gathering information from different places and maybe utilizing journal articles or textbooks as opposed to an ASTM or an ACI standard. These are just some of the references from our research, especially the ones that I touched on in this presentation. And that's all that I have for you. Thank you so much for your time. I'd be happy to answer any questions you have.
Awesome presentation. Thank you, Flint. And I should say this on behalf of the Rock Mechanics Committee. Rock on. So, and I have a quick comment. Who wouldn't want to have their condominium right in front of a rock mass, right? Just a beautiful scene out your back window.
So it's certainly got its pros and cons. You love it when it's there, and you hate it when it's falling.
Exactly. I think I'm going to call on my colleague, Derek. Derek, do you have a question about the presentation?
Yeah, I guess a quick question and then a comment maybe. So the first question is, based on the work that you've done with the aspects of slope stabilization, do you see that also extending into like other measures like rock catchments and other types of systems that we use to manage rockfall?
Yeah, absolutely. I think the beauty of stabilization in general is that it's rarely one technology used alone. You're almost always finding a multifaceted approach to these things. So for many of our case studies, they did utilize catchment devices, different wire mesh to help protect the surrounding areas. And so while you're maybe installing rock bolts or tieback walls into different rock masses, you're also considering different catchment devices. You're also considering how to isolate that area. And so it absolutely is something that extends beyond that even farther. And of course, I could talk about all of that at length too, but then I'm afraid I would bore everyone and this presentation would be much longer than it actually is.
Okay. Yeah, so just a follow-up comment, I guess. I thought it was interesting, your discussion about how cost was difficult to find. And I know a lot of times people turn to geotech tools for information on costs when they're, considering selections and things. So I just thought that was a kind of an interesting observation.
Absolutely. Yeah, we searched quite at length to find different sources that would give us concrete costs, but even as you can tell, one of the ones that we ended up utilizing in our sources was from the 80s. There is some definite gaps in knowledge there. That information just isn't as widespread, and that's something that we would love to have some more information on. And of course, having a full, complete analysis of the cost breakdown for the Geotech Tools technology catalog would be a huge benefit to this project in general.
Cool. Thanks.
Awesome. Thank you very much. And so let's hope we get some questions from the audience as we move to the next presentation. There will be some time at the end of our final presentation for questions for all of our presenters. Our next presenter is Amanda Wachenfeld. And I certainly hope I pronounced that right. And if I didn't, please correct me. She recently graduated from the University of Texas at Austin with a Master of Science degree in geotechnical engineering. She has a lot of work experience and some very cool work experience, right? Another underground person with some tunneling. With this project, she worked with Dr. El Mohtar, who is the chair of the grouting committee. And I know, Chaddy, I mispronounced your name. I'm a little bit nervous. This is my first time on YouTube. And so, Amanda, take it away and tell us about your presentation.
Sure thing. Thank you very much for that introduction. So, yes, I'm going to be talking about the expansion of DIGGS to include soil grouting. And I worked on this project with Professor El Mohtar, as Nick mentioned, with the University of UT. So a little bit about me, kind of in addition to what Nick mentioned. I just graduated from UT in December, hook 'em horns. I have done a lot of work leading up to my time at UT, working in the field in geotechnical and tunneling projects. And during my time in the industry, I actually developed a lot of interest in digital delivery and digital tools to collect data in the field. And that's what kind of led me to help work on DIGGS, which is a digital delivery tool. So a little bit about the project. The goal was to update DIGGS to include permeation and compaction soil grouting. And this included adding new features, objects, and properties into the existing DIGGS schema. And it involved working with the grouting community and the members of the DIGGS committee to complete this project. So a little bit about DIGGS for those of you who might not be familiar. So DIGGS stands for Data Interchange for Geotechnical and Geoenvironmental Specialists. Simply, it is a geotechnical data transfer tool that helps facilitate the transfer of geotechnical and geoenvironmental data within an organization or between multiple organizations. Data is stored in a standardized XML format that can be transferred to a variety of existing software and database tools, such as Gint, Excel, some analytical tools like SlopeW or Plaxis, and this helps eliminate the need for manual entry and re-entry of data. The prior version of DIGGS included schemas or file formats for geotechnical and rock grouting data. So in DIGGS, there are a number of top-level properties under which various data is stored. So in DIGGS, currently we have a property for project information, sampling features such as boreholes, sampling activities such as split spoons, samples themselves such as soil samples or maybe grout mix samples, observations such as soil descriptions, measurements, so any lab testing like grain size curves or monitoring would fall under measurements, and construction activity, which currently in DIGGS consists of grouting, so permeation grouting or rock grouting. And a little bit about permeation and compaction grouting. So both grouting methods are completed in boreholes. Permeation grouting is the injection of a fine grained particulate grout in between the soil particles. So there's no displacement of the particles when doing permeation grouting, whereas compaction grouting uses low mobility aggregate grout to actually displace the soil. So you have a kind of grouted mass and then densified soil around that mass. Even though both grouting methods are used in different soil types and are used for different outcomes, the actual construction and data collected during these grouting activities are pretty similar. So you'd collect information about the pressure or the volume that you grouted, the depth, the similar types of pumps and equipment are used. But the main difference is the type of grout. So for permeation grouting, like I said, you'll use a fine-grained particulate grout or a chemical grout. Whereas for compaction grouting, you'd use an aggregate grout to actually displace that soil. So in order to fully encompass all the information you collect during permeation and compaction grouting, we developed a spreadsheet to identify the type of data that is collected for both of those construction methods. And once we developed a preliminary spreadsheet, I met with individual members of the grouting community to review the spreadsheet and add any feedback they might have based on their unique project experience. And this allowed us to make sure that the list of information we had was truly comprehensive. So it would include information that you might typically collect on a project, but also ones that you might not typically collect, so we can ensure that DIGGS is fully comprehensive. That final spreadsheet was then sent to the whole ASCE grouting committee for their input. And once we got feedback, we used that list to update DIGGS. And this included modifying the existing rock grouting schema and reorganizing some properties and projects within DIGGS to better encompass the soil grouting information. So this is our updated DIGGS structure based on the feedback in our final spreadsheet. So this is a generalized data model showing the relations between the new grouting objects, which are in red, and the associated existing DIGGS objects, which are in black. This is not everything that is in DIGGS, but just what's related to the grouting schemas. So one of the main changes we made was to the rock grouting activity object, which falls under our construction activity property. So this includes all information related to a grouting activity, so general information, grout stage information, which is the range of depths that you are grouting at a specific time, and then the injection time series information. So originally this was just called rock grouting activity because it was the only grouting that was in DIGGS, and we replaced it to just be grouting activity, and we slightly modified the related objects and properties to allow for all grouting activities that take place in a borehole to be saved in this grouting activity object. We also added additional objects and properties to this activity, such as additional equipment information to encompass all the equipment that might be used for permeation, compaction, or rock grouting. And we also added other information such as stage termination criteria, which for soil grouting could be a pressure limit cutoff or a volume limit cutoff or ground movement. So all that type of information that's relevant to the soil grouting was added to this grouting activity, which can now be used for any downhole grouting construction activity. Next, we made changes to the grout mix object. So originally, there was a property in grouting activity called grout mix, and we moved that to a standalone sample feature because that's more consistent with the activity that produces a grout mix, and it gives us more flexibility to associate testing with it. So you can see that here, like all these material tests are now associated with our grout batch information. We split the grout mix into two objects, a trial grout batch, which is information about the mixes that are made to develop a mix design, and a grout batch, which is actually the information about the production grout that goes into the ground. Both of these objects contain the same properties, but the grout batch includes a reference to a design mix, and is referenced to this actual grouting activity. We also added additional objects and properties to these objects, and we added information that would allow for you to add data for low mobility grout and chemical grouting to encompass the type of grouts that you would have for permeation and compaction grouting. We also added these material test objects, which, as you can see, can be referenced to the grout batch and the grouting activity. Originally in DIGGS, there was just a test object, which related material test to a specific location, so such as a soil at a certain depth at a certain location, or monitoring, which just related a test to a specific time. So this material test now allows us to relate testing to a specific sample, which is needed when testing grout batches. So this allows us more flexibility to reference samples for different tests. So we can reference our trial grout batch, our grout batch, or a specific specimen from either of these. And we also added all these tests in red. The only test that existed in DIGGS before was the unconfined compression test, and all these other tests were added to encompass the testing that's done for the grout for permeation and compaction grouting. Finally, our final big change was the addition of a program property. So if you could think about the initial list that I mentioned, it did not include this program property. So this is a totally new property that we developed as part of this project, and it's not just specific to grout. So this will allow users to store any specification or design information that's developed prior to construction, or if you're doing a geotechnical investigation, prior to your site investigation. Currently, we have a grouting program object, which includes design grout mix, grout specifications, grouting activity specifications, and grouting performance specifications. And having these in this program spec or program property allows you to reference your design or specification throughout your other objects in DIGGS. So your design grout mix can be referenced in your grout batch object. So you know like what your design strength is, and you can see if your testing is actually getting you to that design strength. The grouting activity will reference the grouting activity specification, and the grouting performance specifications can be related to geotechnical testing that you do post-construction to verify your grout program. So I just want to show a little example of what the schema looks like and how like you can transfer between Excel and DIGGS. So this is a example compaction grouting log. So you have the time and date, the depth of each stage, your min and max pressures, your pump strokes, and your cumulative volume. And in the comments, this relates to the termination criteria I mentioned. So I'm just going to go through this first stage, which is grouting from 11 or 12 feet to 11 feet because we're going from the bottom up. So we'll look at this piece of data first. And this is our DIGGS schema. So here you can see we're talking about a grout stage, and we've named the grout stage 1. And here we can put in the linear extent, so 11 to 12. Next, we're looking at the time that it was pumped and the min and max pressures. So here we have a property called max injection pressure, and we have 75, and then min injection pressure is 50, and the start time was 1546. And finally, in our Excel file, we have the number of pump strokes, the volume, and the termination criteria, PCO, which stands for pressure cutoff. And so here our delivery, well, in that we didn't have delivery type, but other information would give us that the grout was delivered through casing. The injection termination was by the pressure limit, so the PCO. The number of strokes was 11, and the total grout take was 2.7, and then here's the units, cubic feet. So it's, I know, a little much to look at an XML format, but the nice thing about DIGGS is that you don't need to manually enter things into this XML format. You can use data converters to convert from XML to Excel or Excel to XML and share that, and then use that XML file in any other kind of database you need. So that really minimizes the need to type in or like copy and paste multiple cells and rows into a different database when sharing or storing data. So DIGGS is still improving. The development of that program feature is definitely ongoing. There's a number of things that during my time on the project, I noted that we need to include that we didn't actually have time to get to during my time working on the project. So that includes adding proposed grout hole layouts, adding post-construction verification comparisons to confirm that the actual grouting program did what it was supposed to do, and expanding that program level to include information for geotechnical and rock grouting projects. So even though that type of data is already in DIGGS, because this program feature is new, it's not in there yet. Additional objects and properties will also continue to be added to DIGGS as additional grouting techniques are added, such as jet grouting. And I know that there's also work to add additional underground construction data schemas, such as like foundations, into DIGGS. So thank you to the Geo-Institute and the Grouting Committee for the opportunity to work on this project. And a big thank you to all of those listed here for their time and input during this project. It was very helpful to speak with all these people when developing our list. And a big thank you to Dan Ponte, who actually helped a lot with the coding, or did all the coding for DIGGS based on that spreadsheet. So thank you to all these people, and thank you for listening. And if you are interested in more about DIGGS, please check out this website. There's a lot of past information and like webinars and training videos on that website to teach you more about DIGGS if that's something you're interested in.
Awesome. Thank you, Amanda. What a wonderful presentation. I have a question for you.
Mm-hmm.
And in your presentation, you mentioned that you met with members or people associated with the grouting community.
Mm-hmm.
Did anyone give you a blank stare and say, what's DIGGS?
Yes, a lot of people did actually ask, what is DIGGS? What is this? And, you know, I did my best to explain it to them. A lot of people, it seems to think that it's like a standard for how or like what data should be collected in a project, but that's not true. We're not telling anyone what to collect. It's, if you collect this data, you can save it here. So that was like the biggest question that we had to answer was, is this a standard for what data to collect, or a standardized like file format for the data you collect, which is, that's what it is. And it's not a, we're not forcing anyone to collect a certain way, like a certain set of data or anything like that.
Excellent. And so I have maybe a leading question now.
Mm-hmm.
I know your project was focused on grouting,
Mm-hmm.
and it's very easy to place, you know, where you're grouting in 3D space, right? Because
Mm-hmm.
it's a borehole. With your experience, do you think it's possible that we can relate other geotechnical aspects into DIGGS? So if we talk about maybe there's a landslide occurring, how would we, how would we incorporate that spatially into DIGGS?
Yeah, that is definitely a challenge. The nice thing about DIGGS too is that you can really link anything. So if you have like a file, a file with 3D points, that can be put, not currently, obviously, but hopefully the goal is that that could be, you know, put into DIGGS. So it should, you know, as it develops, and a lot of these things will come, like when people start, I think when the industry starts using DIGGS more readily, will be, the people who work on DIGGS will be able to see, you know, this is the type of stuff that we need to include, and this is how we need to format things and stuff to like hopefully be able to encompass all that type of geotech information.
Awesome. Thank you very much. Now, I know my colleague Derek has a burning question.
Oh, okay.
DIGGS. Derek, go ahead.
No, I was just going to say, from your experience on the project, did the time frame of a year, you know, seem suitable? You know, because I'm just curious as to like the level of effort to get,
Sure,
you know, the schema. Yeah,
so for this specific project, I do think it was reasonable, mainly because the rock routing information was already in there, and when we were looking at the type of information we needed to include for the soil grouting, we didn't need to add a ton of new stuff in order to include that. So thinking about that in terms of a year, I think it was the right amount of time. But if you're starting from scratch for something such as, like I mentioned, I know that like the deep foundations are trying to add foundations into DIGGS, that might be harder because you don't have a jumping off point as well established as we did for this project. So that one, maybe 2 years you might need. So I think it kind of depends on what you know, what you're looking to include and what is already there for you to springboard off of.
Okay, yeah, thanks. Because right now we've got a project where we're starting to look at incorporating geophysics into DIGGS, and there's also some look at incorporating construction of driven piles as one of the next opportunities. So
right. Yeah, I feel like the geophysics, we talked about that actually during this project as well, because you use geophysics to, you know, for many reasons, but as one of our like post-grading verification testing in our list, we had geophysics, and I feel like that's is a nice thing to add to DIGGS for sure.
Cool. Well, thank you. Great presentation.
Yep, thank you.
I very much enjoyed all three presenters and hearing about some of the things that are related to GI's special project initiative. So thank you.
Yes, I'd like to echo Derek's sentiments. Thank you to the three presenters that we had. Very interesting presentations, and our special projects program is a yearly event, and so we're looking for our technical committees to submit proposals for special projects to the Technical Coordination Council. And we will have, I believe we're still going to have our kickoff meeting to special projects later this year in the summer sometime. There's no other questions in the chat. So I would officially like to thank our three presenters for their time and their efforts and for all of their help promoting the Geo-Institute. Derek, any final words from you?
No, I think I would just say I appreciate everybody joining us today. And when we go into reruns, look forward for more information on the third episode of our student research web series. So more to come. So thanks to our speakers and our audience. I appreciate you taking the time to be with us and tell about special projects this go around. Thank you.
Thank you, everyone.